Now see a hysteresis curve. Hysteresis curve is actually relation between I and H for the ferromagnetic material. So now if you have taken a ferromagnetic material and placing in an external magnetic field or the magnetizing intensity H, and this ferromagnetic material is magnetized. So see here the behavior of this, how is it magnetized, and now if it is demagnetized, everything is represented by this IH curve, and this form the loop is here between I and H in the complete process of magnetization and demagnetization of the ferromagnetic material. So this curve is actually representing magnetization and demagnetization of the ferromagnetic materials. Now see here, from here if you are starting, H is 0 and no I is here. As you increase H, I increases like this, it goes linearly like this is here, and after some time it attains saturation here at this point. So when the saturated magnetic field is obtained, then H is reduced. So now you start reducing H. When you reduce H, so this I also reduces, and now when H is 0, I is in the material is not 0. It has got this much value that is equal to A. It means when external magnetic field is 0, but the magnetic field inside the ferromagnetic material is not 0. That means this is a residual magnetism, and this is known as actually retentivity. So OA is actually, that is OA is a residual magnetism, which we can call it is here, that is here retentivity. Now if you reduce, apply H in opposite direction to this side here. So at the point B here, I will become 0. So this is the value of H in opposite direction to the previous one, where intensity of magnetization or I has become 0. So this OB is known as here coercivity. And now when you increase this value of H in opposite direction, here it magnetizes to this point, and again it gets saturation, but in opposite direction. Now again you start changing the direction of the H and its magnitude. So you will be getting, again it happens here when H is 0, this is here, that we can take as C here. So this OC can be taken as here again the retentivity, and now this is the D point, again OD can be taken as a coercivity. So this IH relation is actually completely representing magnetization and demagnetization of the ferromagnetic materials, and this loop is known as hysteresis curve or hysteresis loop. Area of this loop actually represent energy loss. Larger the area of this hysteresis loop, larger is the energy loss in the process of magnetization and demagnetization. Now see here, permanent magnet and electromagnets are made here by keeping all these property like retentivity, coercivity and mu r everything in mind. So now see what are the properties required for making the permanent and electromagnets. So now see here, what are the properties of the materials required for making permanent magnets? First one, it should have high retentivity, high coercivity and high permeability. And also for the electromagnets, the material should have high permeability and low retentivity. So when you switch off the current and suddenly it gets demagnetized, because we don't need the magnetic property after the current is switched off. So the electromagnet should have the low retentivity. So if you take a material like a steel and the soft iron, out of the steel and soft iron, the soft iron has got a high retentivity and the low coercivity also here. So but it is not preferred for making the permanent magnet, whereas steel has got comparatively low retentivity but a high coercivity. So for making the permanent magnet, steel is preferred, whereas for making the electromagnet, the soft iron is preferred.